Okay, so we say that under unsupervised learning technique, we actually had three types of three methods. Number one was the clustering, number two, the association, and now number three is what we call the dimensionality reduction. Now, when it comes to clustering, we were grouping together data points with similar characteristics or based on differences. But when it came to association, we were trying to mine or trying to find out the frequent item sets that are purchased together, or basically it is applied in a retail basket. Now, in dimensionality reduction, like the name suggests, the dimension of a data is always how wide the data set is. So when you talk about the dimensionality reduction, it is probably to bring us to the point that we are trying uh, to get the most important features from the most important features or the most important column from the wide data set. Now, dimensionality reduction is a very important one, and the reason why it's a very important one is because it applies practical mathematics and statistics to ensure that we end up with the important features. So dimensionality reduction is an unsupervised learning technique that reduces the number of features or dimensions in a data set. For example, you can have 40 columns, but out of these 40 columns, you are only interested in finding the two most important features. So these two most important features can only be found by dimensionality reduction. So more data is generally better for machine learning, but it can also make it more challenging to visualize the data or work with the data. So dimensionality reduction extracts important features from the dataset, reducing the number of irrelevant or random features present. So the irrelevant features which are not most commonly needed are done away with or are ignored, while the most important features are taken into consideration. So there are two types of unsupervised learning algorithms under dimensionality reduction. We have what is called principal component analysis using singular value decomposition, SVD. And this is the one we're going to look at in this reading. Then we also have factor analysis, which I always tell my students to do more research on. Personally, I've never touched on it. I will use principal component analysis. So principal component analysis, PCA, this one was in my last paper exam and it was 20 marks. Yes, they just gave us 10 column data with 10 rows. Then they tell you to perform principal component analysis 20 marks and you start seeing stars. And it was a compulsory question number one. So there was nowhere to hide. And he prepared us mentally, by the way. He told us that our exam will have a machine learning task. So we prepare well. People are looking for linear regression, nini. But we were lucky enough to also have revised with my friends the previous night principal component analysis. Though I'm pretty sure I did not get the full 20 marks, especially after coming to, though your course in Patanga A, but especially after coming to your unit, I mean, to work and doing more research and seeing how it is done, I just concluded to myself that I didn't get the 20 marks. So PCA is a statistical technique that employs statistical measures such as mean, standard deviation, and standardization, together with mathematical functions such as linear algebra matrices and eigenvalues to eigenvectors to reduce the dimensionality of large data sets, increasing interpretability while at the same time minimizing information loss. We are not losing any information. What we are only doing, we are just working with what is more important to us. The ones that are less important are ignored, but we are not losing any information. And we are using the most practical way to do that. And the most practical way is by finding mean, standard deviation, and standardization. Then combining it together, which we're going to see how it is done, with linear algebra, linear algebras matrices, and eigenvalues or eigenvectors. So the new variables that are constructed as linear combinations or mixtures of the initial variables are called principal components. So the new variable that we come up with, or we are now using to base our argument, or we are now using to make conclusion, are called principal components. So you can be given a very large data set to analyze, then you are told to find the principal components. In short, they're just telling you to find the most important features from the data set, which can now be used to make conclusions. And in this case, let's say you are recommending, you can now recommend the most important features. These principal components can be projected onto the initial data points by a method called projection, which we're gonna see later in the course. So steps involved in PCA. Hey, this one is a very small data set, but it's actually a 2D. But I want to tell you that it is going to involve a lot, and because you're going to work with a very large data set, so you want to see the most important features between the two. So we have given the following data set, ID1 for the variable x1 and variable x2. So we want to find the most important features of the principal component between the two. So the steps involved in PCA involves the following. Given a data set, number one, you calculate the mean. Then, which means that if you have a categorical data set, then you cannot calculate the mean that way. So what do? You perform scaling and encoding. So you might want to perform one hot encoding is when, like, I mean, you must work with numerical data. That is a must. It's a must. There is no negotiation about that. So if you have a data set that is more of categorical data set, it is advisable that you encode it first, then you scale it. Then after scaling is when you start from where we want now to start. You calculate the mean. So when you calculate the mean of each variables, variable x1 and x2 is basically adding up, the summing up the value of the variables, then divided by the number. Like in x1 is 1 over 4 of the sum, which is 8, then x2 is 8.5. That is step 1, you are done. It's by as easy as ABCD. Then step 2, you calculate the covariance matrix. So, and this covariance matrix is called X. Look at that, covariance of x1, x1, and covariance of x2, x2, that's basically 1. Then the covariance of x1, x2 is equals to covariance of x2, x1. And how do you calculate the covariance of x1, x2? The formula is given there. It's always 1 over n minus 1. Summation of from k equals to 1 to n of x1k minus x1 bar, which means the means, which means that you take all the values of x1 minus the mean as you multiply, as you sum, times x2k minus x2 bar. So from here, I cannot teach mathematics as if I'm teaching theory. So itabidi tumeanza sasa kucalculate. So we have 4, 8, 13, 7. Mean was found to be 8. Then we have 11, 4, 5, 14. 11, 4, 5, 14. And the mean was found to be 8.5. So covariance of x1, x2, which is actually the same as covariance of x2, x1, is given by summation all over 1 minus n minus 1, 1 all over, summation of k starting from 1 to n of x1k minus x1 bar times x2k minus x2 bar, where k is just the position of the element in the table. So when you do this, you most definitely gonna have 1 over 4 minus 1 into, so 4 minus 8 times 11 minus 8.5 plus all the way up to the last one, which is 7 minus 8 times 14 minus 8.5. So this one will yield the following: negative 11, negative 11. That is the covariance matrix. So after doing that, covariance of x2, x1 is also negative 11. Then you calculate the covariance of x1, x1, and the covariance of x2, x2. That one, sorry, I see this one. That's wrong. That is when you, after scaling, is when it comes one. I think we are headed there. So covariance of x1, x1, the same thing, just that we've now changed position, is 1 over 4 minus 1 into, but now we use explicitly, in fact, let me just write the formula so that it makes sense. When I was telling you that it will come back to haunt us, the statistics for data science, you thought it was a lie. So here what you do is just x1k minus x1 bar squared, because we're just using the same column, which basically means it's 4 minus 8 squared plus 8 minus 8 squared, 13 minus 8 squared, 8 minus 8 squared plus 13 minus 8 squared plus 7 minus 8 squared. Then you divide by 3. So this one becomes, that one becomes 23. So covariance of x2, that is x2, x2. Okay. The one I was doing is for x1, x2, so it's not 23. It is a certain value. Then covariance, when you do the same thing using row 2, it becomes 23. Then you now form the covariance matrix from this information. Remember, covariance of x1, x2 is the same as the covariance of x2, x1. So you end up with the following information. Covariance of x1, x1 is 14. Covariance of x1, x2, which is the same as covariance of x2, x1, is negative 11. And the covariance of x2, x2 is 23. So we are done with step 2. Step 1 was you calculate mean, then step 2, use the mean to calculate the variance covariance matrix. Is there any question up to that point? Then number 3, where the road starts becoming a SGR, is when we should calculate the eigenvalues and the eigenvectors of the variance covariance matrix. This is where things starts going hayway. Ha! So for us to get the eigenvalues, we need to find a lambda, a value of a lambda, and eigenvalues are like, I do not necessarily want to term them a root of a matrix, but they look like as if they're a root of a matrix, the square root actually. So eigenvalues are those single values that you calculate from a matrix. I don't know, let's call them a root of a matrix, but they are not because they're just eigenvalues. So, but in the sense, for this learning, don't say that in an interview setup. Uh, let's look for the information to use from the online. Eigenvalues are special scalar values associated with linear transformation that indicates how much an eigenvector is scaled or stretched during that transformation. Then they can be thought of as a characteristic values of a matrix, revealing key properties. I think you can use the characteristic value not square root, but they reveal key properties of how it affects vectors. So they are special scalar, which means they are a single value. Scalars are single values. So there are special scalar values, and they are associated with linear transformations. So like a matrix. So you must only get them from matrix and indicate how much an eigenvector, which you're going to see is a combination of eigenvalues, is scaled or stretched during that transformation. But think of them as characteristics of a matrix. So in this case, we want to calculate the eigenvalues, and we didn't do this in mathematics for data science because I knew we will find it here. So I'm going to be very, very detailed in calculating it. Now, there is a formula in linear algebra called the eigenvalue formula. It is basically a formula that is at the top. 0 is equal to determinant of S minus lambda I. But what necessarily is lambda I? S, first of all, is the covariance matrix that has been calculated from the given data set. So S is the covariance matrix that we calculated up here, 14, negative 11, negative 11, 23. While lambda I is basically calculating the lambda times the identity matrix. From our linear algebra class, you can remember that the identity matrix, you can remember that the identity matrix I is given by, if it is a 2 by 2 matrix, 1, 0, 0, 1. So, and from our the same linear algebra class, we said that when you multiply a matrix by a scalar like lambda, then basically the scalar is going to multiply individual elements in the matrix. So at the end of the day, we will have lambda 0, 0, lambda, like this. So when we have this lambda 0, this is what is termed as lambda I. So when we take S minus lambda I is basically our variance covariance matrix, which we got, we actually found out before, or had constructed before. No. So let me just open a new one because we'll do the requisite thing. It was 14, negative 11, negative 11, 23. 14, negative 11, negative 11, 23. So it was this way. Now, this is S. When you minus lambda I, which you have calculated to be 0, 0 lambda, from our knowledge of linear algebra, this element here subtract this element here. So we're gonna have 14 minus lambda, negative 11, negative 11, 23 minus lambda. Then the formula is saying that 0 is equals to determinant of S minus lambda I. So which means that the determinant of 14 minus lambda, negative 11, 23 minus lambda should be 0. But what did we say? The determinant, what's the formula for finding determinant of a matrix? This minus this, then you interchange. If you now want to find the inverse, but we just want the determinant. So it's 14 minus lambda into 23 minus lambda minus negative 11 times negative 11 is equals to 0. Let me counter check if that is what, if I'm right. Yeah, okay. Completing the square method, I don't know why I love it from high school. 23 minus lambda, 23 minus lambda, then minus, I think this is 121 now. And this is 0. Then 14 times 23. Very well, is that your calculator? That's okay. That's been It has been in front of me all through. Three 22 minus 14 lambda minus 23 lambda plus lambda squared minus 121 is equal to 0. Actually, this is factorization of completing the square method. So negative 14 lambda minus 23 lambda. Yep, that is right. Plus lambda squared is equal to positive 121 minus 322. So I just want to reorganize things. So lambda squared minus 23 lambda is equals to negative 201. From my little knowledge of completing the square method, yes. Ah, thank you. Thank you. So minus 14 minus 23. That's an oversight, basically. 37. Not wrong. So lambda squared minus 37 lambda. Actually, hata imesaidia juu nilikuwa na skeptical if the square of nini will neutralize to a 1. So the complete square method says minus 37 divided by 2. Sasa nimeandika 33. 18.5 squared is equals to 18.5 squared. That I'm using the completing square method, so you can use quadratic method. Do you remember the completing square method? Do you remember the completing square method in high school? The completing square method requires you to divide the b sinakwanga ax squared plus bx plus c is equal to 0. So the complete square method says that you take ax squared plus bx is equal to negative c. So the constant goes to the other end. Then take a half of b, then add it. If it is minus, you minus. So x minus b all over 2 squared is equal to negative c plus b all over 2. Then you square this one. So, well, I was sharp in maths. So it's English that actually played its game. Okay, but we will be there with it. So minus 201. So lambda minus 18.5 squared is equals to 141.25. So you find the square root of this and you find the square root of this. So lambda equals to plus or minus. So when you get the root of that, this calculator, 141.25. Where the hell is the root? 11.88. Let's use four significant figures. 11.88, then hii sasa inakuja plus 18.85. 18.5. So lambda can be plus 18.5, 30.38, or lambda can be negative 11.88 plus 18.5. 6.62. Hey, let me up. Why am I skeptical about that? Yeah, but the equation is there, so it's definitely gonna yield something. We are right. 6.62 and 30.38. So lambda 1, lambda 2 are given there. Yeah, these are called eigenvector values. The lambda 1 and lambda 2. Up to that point, you will sharpen up to 5 marks and I don't know. Then, but I really loved it. By the way, I hated theory questions. That is now explaining the business side of data science. I really hated those questions in exam, but I really wanted the question that is challenging me. Hey, so that's why I think I loved this principal component analysis thing. Okay, now we continue. From the eigenvalues, we can now find the eigenvectors, which means we bring up another page for eigenvectors. But the things are getting thicker, but I hope up to that point we are together. Yeah. So things are getting thicker. Not thicker now. So we have our eigenvalues. We can now use our eigenvalues to compute our eigenvectors. An eigenvector is, I don't want to call it a combination, but it's basically a transformation of eigenvalues. It is eigenvalues that yields eigenvectors. So an eigenvector is always indicated by letter U, which comprise of values U1, U2, such that 0 into this formula here, 0, 0, S minus lambda hi times U gives you 0. Sorry. Such that S minus lambda I times U. So we can, or V is equals to 0, 0. Which implies that S minus lambda I times U1, U2 is equals to 0. Lakini, which means we are going to have two eigenvectors. Why? We have two values of lambda. We have S, we have lambda, identity I mean, and we have lambda. We have 0, 0. So we can confidently find U. So when you come back here, you're just putting everything in the machine. But there is something that we should not rush to, and this is it. We are required to just explicitly do the things as they are there. We do not necessarily need to fill in the value of lambda at this point, which means we're just going to get a placeholder, and after finding this placeholder, we will just fill in the values, and that's it. We will have the eigenvectors. Then from there, we can now calculate the principal component analysis. So it's a very confusing step when it comes to calculating eigenvectors. So I want you to be very keen, because if you do it directly and fill in these values using the lambda, then probably it's going to be erroneous, which is not accepted. So this is what you do. You put in the value and multiply by U1, U2. Then after multiplying that, you evaluate to 0. Then you're going to evaluate this thing to a certain value placeholder. So this is what I'm trying to say. I'm trying to say that in the previous one, we had S minus lambda I iko wapi? Yeah. Ni hii kweli? No. Ni hii. Yeah. S minus lambda I was 14, this one here. 14 minus lambda, negative 11, 23 minus lambda. So 14 minus lambda, negative 11, 23 minus lambda. But we said if you multiply this with u1, u2, you definitely gonna end up with 0, 0. That is what we said, right? Yeah, but linear algebra tells us that you multiply this row with this column first to get this value. So, which means that you are going to have 14 minus lambda times u1, then it should be plus negative 11 times u2 equals to 0. So, 14 minus lambda u1 minus 11 u2 equals to 0. Well, we can also do this to get this, which we are going to use later to find the value. But again, the rule of linear algebra says even if you use this root times this to get 0, the answer will still be the same as using this and this. So there is no need of repeating yourself in short. So this one guy is enough. Or we might come back to find the second eigenvector using the second value. So we are going to come back to use the second eigenvector. So let's first find the first eigenvector. So depending on the size of your data set, things will get thicker. You can imagine a 4x4 matrix. I think that one cannot be done by bare hands, done by a machine. But the largest that we are given 10 by 10 in exam, we reduce it to covariance matrix of 2 by 2. Then you start from there. Yeah. Which implies that 14 minus lambda u1 equals to 11 u2. If I want to leave this u1 the way it is, then probably I'm just gonna divide by 14 minus lambda over 14 minus lambda. So u1 equals to 11 u2 all over 14 minus lambda, which again you can say u1 all over u2 equals to 11 all over 14 minus lambda. So when you come here, u1 all over 11 is equals to u2 all over 14 minus lambda. I will do the yeah. So since we are interested in either of the two and not all, as that now, because if you find one, you find the other, we cross multiply again. So just to get back to where we were. So it's just trying to say we could have done the other way around instead of doing this according to the formula. But up to this point, this one also works. There is no problem with this. It is okay. Hata tukiacha hapa is equals to t, it's still okay. Just that to align with these examiners' work, we probably need to ensure we are uniform. So when you multiply this, you get from here 14 minus lambda u1 equals to 11 u2. So all of 11 all over 14 all of 11. So u1 all of 11 equals to u2 all over 14 minus lambda. And this one equals to some placeholder t or p, unknown. So this as equation 1 and put it pending. We shall come back to it. I hope you've known how you've arrived at the value of t there. So we derive the eigenvector placeholder formula from the eigenvalues. So u was u1, u2. So u1 over 11 minus u2 all over 14 minus lambda is equals to t. All of them is equal to t, which is trying to tell us, actually, in layman's language, that u1 all of 11 equals to t, semicolon, u2 all over 14 minus lambda is also equal to t. So which is just trying to say u1 is equals to 11t, then u2 equals to 14 minus lambda t. You want to see why this placeholder t is very important. So let's just move. Which means when t is equals to 1, u1 remains 11. And when t is equals to 1, u2 is equals to 14 minus lambda. And for lambda 1, we had 30. If 14 minus 30 is equal to 16, u2 is equal to 16. 40 is equals to 1. Wacha tuache tu hapo, sitaki kuongelea vitu mingi, but mostly we always assign t1. Lakini let's leave at that point. Aya. So look at what has been done there. So u1 or the eigenvector 1 is equal to 11 and 14 minus lambda. What have we done? We've taken t is equals to 1. So what I was talking about, when t equals to 1, then eigenvector 1, eigenvector u1 equals to 11 for u1. Okay, African 1 to see, which equals to, and 14 minus lambda. So this is the first eigenvector. It's not explicit, but remember we are coming back to just add the details of lambda there. Let's find a unit eigenvector. To find a unit eigenvector, we compute the length of u1, which is given by u1 is equals to 11 all over the absolute value of u1 and 14 minus lambda 1 all over the absolute value of u1, where the absolute value of u1 is always, I don't want to call it absolute, it's not absolute value, but how can I call it? If you are told to find, there is a name, where am I? Let's ask AI. There's a name for this. Gemini excels in maths. Let me tell us the name. Given a matrix U, what do we call U that involves finding square root? Of the combination of its scalars. The norm mu is called the Frobenius norm. It's essentially like treating the matrix as a long vector and calculating its Euclidean norm. I'm not there. I'm not a mathematician, but Gemini excels in maths. Okay, so the norm of that vector. So to find a unit eigenvector, we complete the length of mu1, which is given by that length there. Then you take eigenvector 1 to be 11 minus. So from here, we are not yet done. It means that eigenvector 1 will be 11 minus the norm of mu, then 14 minus lambda. I was looking for the name. The Euclidean, not distance, but the Euclidean value of that vector, mu. So this one will be E1. Which means that, so when you calculate absolute value or a norm of mu is given by the value squared time plus the other one squared, but you find the square root. 11 squared plus 14 minus lambda squared. Let's find for eigenvalue 1, which it means for lambda 1. So for lambda 1, which was 30 points from the previous calculation, I hope I've not lost you anywhere. Kizungu najua imekuwa mingi sana. 30.38. 30.38. So lambda 1 is 30.38. 11 squared plus 14 minus 30.38 squared. Then square root of this. You remember what we are doing with the Euclidean distance? So we are borrowing the concept there. The distance between the vector and it. Then squared. Answer plus 11 squared. Then square root of answer to get 19.73. To 4 decimal places to be somehow precise. Then we are being told that what you do, you now say eigenvalue 1 is equals to 11 all over 19.7308. This is a formula. Even if you ask me why, I don't know, it's a formula. Then 16, Jesus Christ, negative 14 minus 30.38, negative 16.38 all over 19.7308. Then the eigenvalue 1 becomes this one here, 0.5574, negative 0.8303, 5574. The one for 2 also follows the same formula, except that the only thing that changes the only thing that changes is that we now use the eigenvalue 2. And what is the value for eigenvalue 2? We come back here, 6.62. So we just say absolute of norm. Hey, why do you use norm of mu2 now becomes 11 squared plus 14 minus 6.62 squared, which is equals to, so 14 minus 6.62, answer squared, plus 11 squared, divided by square root of 13.2463. 13.2463. So again, E2 is equals to 11 all over 13.2463. Then 14 minus 662. 14 minus 6.62. 7.38 all over. At this time now you are over 10 marks, I'm very sure. All over 13.2463. Then eigenvalue 2 becomes what is there? 0.8303 and 0.557. And I hope you've seen a pattern there. 0.8303, 0.5574. These are the eigenvectors. So eigenvector 1 is here, eigenvector 2 is here. Now, from these eigenvectors, remember, mean was used to calculate the variance covariance matrix. The variance covariance matrix was used to calculate the eigenvalue. The eigenvalues were used to compute the eigenvectors. Now the eigenvectors are being used to do what? Calculate the principal component. And the principal component is given by the following formula. The principal component is given by the following formula: eigenvector 1 transpose linear algebra tupu. So principal component is equals to eigenvector 1 transpose times x1k minus x bar, x2k minus x2 bar. If I'm not wrong, let us verify. Yes. So which means that it is actually the transpose. The transpose meaning that if it was this way, you should now put it this way. But eigenvector 1, what is the value of eigenvector 1? 0.5574 negative 0.8303. 0.5574 negative 0.8303 minus times x11. When k is equals to 1, this one becomes x11, this one becomes x21. Then minus x bar 1 minus x bar 2, which in layman's term 0.5574 0.8303 times x11. We go back to the data set where x11 is. Yeah, x11 ni hapa, the 4, this one here, and x21 is this. Then x12, x22, hivyo hivyo. You now calculate for each and every value. Yes. Actually, when you minus 8, then this one becomes, hiyo ingine ni 11 minus 8.5. They form one matrix that way. So, which means that this is 4. So allow me to just know that this is 4 and this is 2.5. For 2.5. Mathematicians are always sure. Minus 8.5. 11.5 minus 11. Was not wrong. 11 minus 8.5. Anyway, divide. Hii calculator yako beril hapana. 8.5. Hii ndio unataka kwenda kufanya mtihani, I'm sorry. So we have 0.5574 times 4. 2.2296, 2.2296 plus 0 negative 0.8303 times 2.5. So plus 2.2296, 0.1539. It is 4 minus 8, Jesus. I'm wrong here. It should be negative 4. So this one becomes negative. So plus negative 2.20 something. So it becomes negative 4 points. So that is here. Wait, you see one mistake like that and everything is wrong. Okay. Then that one is is for 1. You will do for the other values. You will do for other values. Yeah. Then you now have the table for first principal components for all values. The first principal component for all values is when you use eigenvector 1. Then the second principal component is when you use eigenvector 2. Are we together? Ama nimekupoteza mahali? Wapi? Oh, Paul, I'm saying the first principal component is when you use eigenvector 1, which you are using here. Then you will do the same thing for all the values. Look at the feature x1, x2. When you calculate for 4 and 11, you get negative 4. Yes. Then for 8 and 4, for 13 and 2, that is first principal component. Then the second principal component, allow me to do one so that at least you get to know what I'm trying to say. So is when you use eigenvector 2 now. And our eigenvector 2 was 0.8303, 0.5. Pardon? The entire values again. What you are doing with eigenvalue vector 1, except that you now change it to, so when you transport it is 0.8303, 0.5574. Ni nani ya huyo? Check it. May you kindly call later? I'm actually at work. Yeah. Okay, Bell, can you power on this, please? Your Wi-Fi. Okay. Sorry, I know you lost me. Are you there? Sorry, I know you lost me. Someone called and it disrupted my internet. Actually, the internet providers themselves, they are to help me troubleshoot it. Right now, I'm using hotspot. Okay. Now, then times, you do the same thing. What was done on earth must be done in heaven. So -4 and 2.5. So the second principal component will be 0.8303 times -4. So -3.3212, which is against how you should pronounce values after decimal, should be -3.3212. Then plus 0.55274 times 2.5, 1.3935, 1.3935. So when you add the -3.3212, you get -1.9277. So the second principal component, it will be here, just below the first principal. It will be after -4.30, you go to negative 9.1.9277. So even until they are done for example 4. So you can imagine a large data set. We're working with the two. It depends with the number of eigenvectors, which is also depending with the number of with the size of the variance covariance matrix. If the variance covariance matrix was a 2 by 2 matrix, 2 eigenvectors. If the variance covariance matrix was a 3 by 3, 3, you go even until you find 10. So who goes beyond the 10 way? When you plot the values with the mean point, you know what? Our main interest is to find the principal component and the feature that is most important. So when you plot it with the mean point, this is how the graph appears. Look at the value that is closest to the mean point. When you project it now, when you project it to the mean point is 8 and 8.5. You remember that, right? Now the respective the individual values of 411 as detailed here: 411, 8, 4, 3, 5, 13, 5, 7, 14. So the principal, what is the principal the one that might be principally, I think, look at the value of 8, 4. It is somehow closer to the mean, and that is the important feature. So when you are recommending, if it was a product, you will recommend product 8, 4, because it has the least positive 3.37 to 7361, and it is closer to the mean. Yeah, so that is it. And this is what we are going to build tomorrow. Unfortunately, we can't build it. I wanted us to build it today, but my sister has an exam at 11. I want to give her a machine to prepare. Yake imeharibika. Aya, real world and supervised. Yeah, yeah. By the way, sorry. Ask. 84, 84. Yes, and that's especially when you project E1 and E2. Remember, how do you know that you are projecting E1 and E2? We are just trying to look at the principal components here. So when you look at the principal components, is at negative 4.3052. Then for 84 is at 3.37. So the principal component for E2, where it is coming from, it is coming from the negative side of it. Sorry, I'm trying to, yes, that is. But let me go and do the one on a data set, then find the best explanation, then we will the best conclusion, then because it's the real world example one. But that's how principal component analysis is done. You first of all calculate the mean, use the mean to calculate variance covariance matrix. Then use the variance covariance matrix to get the eigenvalues. Then use the eigenvalues to get the eigenvectors by inputting a placeholder t. Then use the placeholder t to get a norm. Then use the norm to now calculate the eigenvectors. Then use the eigenvectors to find the principal components. Then project the principal components and evaluate against the mean. Then deduce your point. And this is done. The real world and supervised learning examples, anomaly detection. We always want to see the abnormal transactions in a bank. Recommendation engines, the best features that can be recommended, the principal components, and I think it can excel in recommendation engines. They're calling again. I don't know. Okay. Can you hear me? Pole sana. Sasa hii kitu inafanya inaanza kumisbehave. Customer segmentation, that one we saw, it is actually for clustering. Fraud detection, we also saw that with the banking fraudulent detection. The natural language processing, then genetic research. Okay, this natural language processing, put it pending because we are going to use it sana sana on deep learning. Genetic research, then that's it. So when it comes to anomaly detection, unsupervised clustering can process large data sets and discover data points that are atypical in the data set. May you kindly tell us what algorithm can be used for this? What algorithm did we say is able to cluster even the outliers? Not really. The DB scan. You remember when which can also form an outlier for -1. So and it can detect anomaly. The number two recommendation is engines using association rules and supervised machine learning can help explore transactional data to discover patterns or trends that can be used to drive personalized recommendations for online retailers. Then customer segmentation. Unsupervised learning is also commonly used to generate buyer persona profiles by clustering customers' common traits or purchasing behaviors. These profiles can then be used to guide marketing and other business strategies. Fraud detection and supervised learning is useful for anomaly detection, revealing unusual data points in data sets. So anomaly detection and fraud detection are the same thing. These insights can help uncover events or behaviors that deviate from normal patterns in the data, revealing fraudulent transactions on unusual behavior like bot activity. Are you? Can you hear me? Ama, you've lost me. Okay. Natural language processing unsupervised learning is commonly used for various NLP applications, such as categorizing articles in news sections, text translation and classification, or speech recognition in conversational interfaces. So, for categorizing articles in news sections is basically, for a company, a news company use an NLP, then it means a very big news company. So, you also have genetic research. Genetic clustering is another common and supervised learning example. Hierarchical clustering algorithms are often used to analyze DNA patterns and reveal evolutionary relationships. Then that marks the end of dimensionality reduction and unsupervised learning technique. On Monday, we are building it, then beginning on reinforcement learning. So once we're done with reinforcement learning, we will take a 2 weeks break, alafu tuturudi tumalize the course. So reinforcement learning is basically where there is an agent and an environment. An agent tries to learn from the environment and optimize. So by the end of the day, it gets rewards when it does the right thing and gets penalized when it does the wrong thing. And that's why self-driving car is becoming a success because of reinforcement learning. But we are going to talk about it and see the algorithms that are used to develop self-driving cars. But up to that point, we can stop for today, unless you have any other question. All right. Kwanza hii wifi inatengenezwa, acha nizitumie ku upload. No uploading those things with bundles, we. But be reminded on that. Sasa we can meet